Hello and welcome to session number 7. This time we're going to be summarizing again intrinsic and doped semiconductors. We'll probably take one more shot at this in our next session. We'll be looking at degenerate doping, what it means, why it's important, and then we'll be looking at the 3 probability distributions, the classical Boltzmann and the quantum Fermi-Dirac and Bose-Einstein. And then finally we'll be ending up with some examples. It is said that if you want to start a revolution, more than a set of grievances, slogans, placards, you need a song. And we're going to be listening to the song that started a revolution, stopped a war, made us all better than we were before. Its composer won the Nobel Prize in Literature a few years ago, and I hope you may have guessed that we're going to be listening to Peter, Paul and Mary singing 1965 version by Bobby Dylan, Blowin' in the Wind.
This song asks 9 questions. The answers to these questions could determine the fate of all of us in this next generation.
The cannonballs fly before they're forever banned. The answer, my friend, is blowing in the wind. The answer is blowing in the wind.
How many years can a mountain exist before it is washed to the sea? How many years can some people exist before they're allowed to be free? How many times can a man turn his head and pretend that he just doesn't see?
Take till he knows that too many people have died.
The answer, my friend, is blowing in the wind. The answer is blowing in the wind. The answer is blowing.
Okay, this is a kind of a rough outline of the topics we'll be covering today. Let's jump right into the intrinsic. And here is a band gap, energy band gap diagram for silicon in its intrinsic state, if you will. The total band gap, or the band gap EG, is the difference between the conduction band and the valence band. For silicon, it's 1.12 eV. One half of that is the intrinsic level, and that is 0.56, which is right in the middle of the energy band diagram. The Fermi level for intrinsic semiconductors is always at the intrinsic level. In fact, it is pinned to the intrinsic level, which means that for low temperature, where is it? Right in the middle. For high temperature, also right in the middle. Doesn't matter what the temperature is, the Fermi level is right in the middle of the energy band diagram. The number of electron hole pairs depends primarily, I would say exclusively, on the band gap and the temperature. The band gap, because the larger the band gap, the harder it is to make that transition. I can jump a half a foot, but 5 foot, that's a little bit hard for me. Tin, for example, is a semiconductor with a very small band gap, so that even at room temperature, there are enough thermally generated electrons and holes to make it conduct electricity quite readily. But it's still a semiconductor. Small band gap, easy to make the transition. Large band gap, harder to make the transition. Temperature, when we get up in the morning, before you had that first cup of coffee, you're kind of sluggish. Once you have that cup of coffee, you're energized, and in the case of intrinsic semiconductors, for higher energy, they've got more energy in the lattice vibrations, and it's easier to make that transition from the valence band into the conduction band. We represent this quantitatively by a equilibrium chemical reaction. The left side are the reactants. These are the electron hole pairs which are bound to the lattice. On the right side we have the free electrons in the conduction band and the free holes, or the mobile holes, in the valence band. In doped semiconductors we have something very dramatically different. The number of products is dramatically increased, which shifts the reaction to the left. It stresses the reaction, and the Chatelier's principle tells us that a reaction which is stressed will conduct itself in such a way as to try to reduce the stress. Guess what? You and me act the same way. When we're stressed, we try to reduce the stress. In our case, we can either take drugs or we can listen to Mozart. Personally, I prefer the Mozart. Okay, and the last session, we derived this very important reaction, or very important equation, I should say, relationship between the number of electrons and the number of holes for an intrinsic or for a doped semiconductor is equal to the number of intrinsic semiconductors squared. The only issue here is that we have equilibrium, and we'll talk about what equilibrium is in our next session. But anyway, for intrinsic, the number of n is 10 to the 10th. The number of p, 10 to the 10th. 10 to the 10th times 10 to the 10th is 10 to the 20th. For a doped, let's say a donor doped, at 10 to the 15th, n is 10 to the 15th. Therefore, p must be 10 to the 5th, because 10 to the 15th multiplied by 10 to the 5th is 10 to the 20th. Now, for a doped semiconductor, our goal is to find how far the Fermi level is from intrinsic. And you look at this and you say, well, the intrinsic is pinned at the, always at the midpoint. The Fermi level is above the intrinsic, so therefore we suspect, and we're right, that the semiconductor is donor doped. Now, the relevant equations are, for intrinsic, the n sub I is given by functions of the band gap and temperature, and that's it. This is the mass of the electron or the holes changes slightly from semiconductor to semiconductor. For doped semiconductors, we're going to write two equations. We're not going to derive them. We'll derive them in our next session. But for now, we're going to use them using the principle of quantum mechanics, which that rather horrible expression, shut up and calculate. So we're going to just calculate these values using these two equations, and we'll see how that works. First equation references the number of electrons to the intrinsic. The second equation references the number of electrons to this rather interesting number n sub c, and it's going to work out that n sub c is, where is n sub c? N sub c is this right here. All of this will be n sub c without this exponential term. So we're going to reference the number of electrons either to intrinsic or to this number n sub c, and we'll talk a little bit more about that as we proceed. The critical issue here is that for doped semiconductors, donor doped semiconductors, the number of electrons is much greater than the number of intrinsic electrons. The Fermi level is higher, and we'll see what that means in a practical sense. So the basic concepts here are, for intrinsic semiconductors, the important parameters are band gap and temperature. For doped semiconductors, the important parameters are the dose, how many atoms we put in to the lattice for doping, and also the temperature. For example, remember that for doped semiconductors, as we raise the temperature, the Fermi level will fall, and we'll see that in just a little bit. Okay, so let's go back to this equation right here and see if we can take it apart. And we do that by taking the logarithm of both sides, first dividing by n sub I, taking the logarithm. The logarithm of e is 1, so this ratio just falls down. We bring the kt to the left side, and if you're not familiar with this, don't worry about it. We're really only interested right now in the results. What do we want to find? This guy right here, E sub f. E sub f minus E sub I. We know n for a doped semiconductor, it's the dose, and we know n sub I, and we better know k sub t. Remember, that's 0.026. So let's take, for example, a lightly doped semiconductor of 10 to the 15th. So that is the n. We're going to assume that all of the atoms that are put in to the lattice, the doped atoms, the phosphorus atoms, are ionized. So the number of free electrons in the conduction band is 10 to the 15th. So we put that in here, 10 to the 15th. The number of intrinsic, 10 to the 10th, kt 0.026. And we find that this number A, the position of the Fermi level, reference to the intrinsic, is 0.3. So let's go back here. This number A is 0.3. It's a little bit more than halfway, so I didn't draw this very much to scale here, and that makes sense. It's higher than the intrinsic. Now, if we increase the number of doping atoms, increase the doping, the dose, to 10 to the 16th, we would find that the Fermi level is now raised up further. You know, as we increase the doping, the Fermi level moves up, and it moves up from 0.3 to 0.36, which is to say 60 millivolts, and that's a very important number. Every time we change the doping by a factor of 10, the Fermi level moves by a factor of 60 millivolts, which is why we say 60 millivolts per centimeter. Now, if we increase the doping, and I'm just kind of picking this out, actually not, sorry about that, this is a real number. This is this number right here, 2.8 times 10 to the 19th. If I would increase the number of donor atoms to 2.8 times 10 to the 19th, we would find, well, here it is, 2.8 10 to the 19th, and then blah, 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 push it all through, 0.56. So what happens here is, if we increase the doping way, way up, the Fermi level is now right at the conduction band. And that is a very important value, and we'll be using that quite a bit in coming sessions. Okay, now let's repeat this whole exercise for 10 to the 15th, but now let's use the second equation. Where is the second equation? Must be here someplace. Here, right here. So n sub c is now 2.8 times 10 to the 19th, and let's see what the number of electrons is reference to n sub c. And notice how different these are. In the first case, we know that n is much greater than n sub I, so we like this number to be big, in fact, very big. In the second case, n is going to be less than n sub c. N sub c is way up in the conduction band, so we want this number to be negative. Well, E sub c is high, right up here, and E sub f is low. So this value here is the value we'll be looking for, and E sub f is less than E sub c. Therefore, this number here is in fact negative. So let's put that in someplace. Where is it? Right here. N is 10 to the 15th. N sub c is 10 to the 19th, 2.8 times to the 19th. So we find it is negative, exactly as we would expect, 0.26. If it's 0.26 below E sub c, it is 0.3 above E sub c. Okay, so now let's look at the effect of temperature. Okay, so before we start the temperature, let me do a sanity check. I said it's 0.26 EV below E sub c, which means it's 0.3 EV above, not E sub c, but intrinsic. And of course that all makes sense. 0.3 plus 0.26 is 0.56. Okay, so now let's raise the temperature to 500 Kelvin. Okay, what's 500 Kelvin? It's about 200 C. It's not too much. That's probably, and I'm not a big kitchen cook, but I believe that's less than your oven temperature for baking. So it's probably, I would suggest, the kind of thing that we would see on a junction, perhaps in a transistor. I would suspect could go well above that. So it's the kind of thing that we would see in a laptop. That's why laptops are not supposed to be on your lap, because they get hot. And the specific temperatures in the transistors, I would think, could easily rise above 500 K. So we put 500 K into this bad boy. Well, this part of it isn't going to change. It's 500 divided by 300 to the 3/2. It's a little over 2. No big deal. But this part, this part is really going to take a huge quantum leap up, because KT is not 0.026 now. If you put in 500 for T, you get I believe it's 0.043, which means that the intrinsic concentration is, where is it? About 10 to the 14th, actually a bit over 10 to the 14th. So I would have thought perhaps maybe it's a factor of 2, a factor of 3, above 10 to the 10th. It's 4 orders of magnitude, only with a rise of 200 C. Now you can check my arithmetic. I did it a couple of ways, so I believe it's reasonably correct. That's quite remarkable. It really is. Now the Fermi level moves down because we know that when the temperature moves up in a doped semiconductor, the Fermi level moves down. And if we would calculate either reference to E sub I or to E sub C, we would find that we were about, let's see, what is it? I have it right here, about 0.1 eV above intrinsic. Not 0.3, but 0.1. These are very, very dramatic changes. Now, let's increase the band gap from 1.1 eV to 2 eV and go back to 300 Kelvin room temperature. Well, higher band gap, we would think that the N sub I goes down, and we can reference it either to the conduction band edge, which we're doing here, or to the intrinsic band edge. Wow, isn't that cool? We find now that the intrinsic concentration decreases from 10 to the 10th to 10 squared to 100. N sub C doesn't change, not dependent on band gap. But here, this really, really changes, and it changes a lot because instead of having a 0.56, here we have a 1, and that's a big deal. So from 10 to the 10th to 10 squared. And then if we, and I didn't actually perform the calculation here in detail, but if we increase the temperature again by only 200 degrees Celsius, the intrinsic concentration will increase from 10 to the 10th back to 10 to the 9th, almost canceling out the increase in band gap. Okay, finally, we can look at one other little effect which we think should be very small, if at all. The position of the Fermi level for band gap of 1.1 versus 2 for a doping of 10 to the 15th. Now we found that for silicon, the position of the Fermi level is 0.3 eV above intrinsic, while for 2 eV, we find that it rises to 0.73 eV, quite a bit. However, the band gap is also going up. So it's gone from about say 2/3, say maybe a little less than 2/3 to just under 3/4 of the way. A significant change or a finite change, but not really all that dramatic. Okay. Review of doping. We saw this before. You can't see it enough. It's really a big deal. The Fermi-Dirac distribution for N-type and for P-type, the probability of occupancy is always given by the Fermi-Dirac function. However, the probability of ionization is quite a bit different for N-type doped and for P-type doped. For P-type doped, the probability of occupancy is equal to the probability of ionization. For N doping, the probability of occupancy is 1 minus the probability of ionization. Okay, let's see now, where do we go? Okay, so this part here, which you can perhaps review on your own time, basically is an explanation of what this is all about. We've seen it before, so I don't want to take too much time to review things that we've already gone over, but it really is a big deal. Okay, degenerately doped semiconductors. So what is that all about? Well, what it's about is the following. Consider, for example, N-doped. For an N-doped, the Fermi level rises as the dosage increases. Well, it just keeps rising and rising and rising and rising. We keep banging in phosphorus atoms into the lattice until we arrive at the donor level E sub D. And at this point right here, if we go back and look at this, we see that ED minus EF is 0. So this becomes a 1, all of this term, 1 divided by 1 plus 1, or 1 divided by 2. So the probability of ionization, or the probability of occupancy, same thing, is 1/2. 1 divided by 2. Then we keep increasing the dosage by increasing the time. So the Fermi level keeps rising, but the probability of ionization now goes down even further. It's very high up in this area, decreases, 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 becomes 50%, decreases some more, decreases some more, decreases some more. Here it's extremely low. At this point right here, at the conduction band edge, the doping density is approximately 2.8 times 10 to the 19th. Here it's a little bit even higher than that. Why would we want to do that? Because we want to make extremely conductive parts of a transistor. Now, a little story. It's very important. Degenerate doping is something that we do all the time in a semiconductor fab. So when I first started taking over ion implantation, we had quite a number of processes which involved degenerate doping. Now, each wafer took approximately 1 hour to degenerately dope. And you figure if this is a 25 wafer lot, you're talking about over a day's time of ion implantation. Huge, huge issue. Extraordinarily expensive. So I asked the question, do we really need an hour? Now you'd think that the answer would be obvious. Yeah, we need an hour because it has to be degenerately doped. But we don't know that it needs an hour, because if, let's say it needs a half hour. It needs a half hour to get into the same level. What happens to that extra half hour? Well, the probability of ionization is essentially 0. It's extremely small. So we've just wasted a half hour of ionization or ion implantation time. We've done nothing but introduce phosphorus atoms which are not being ionized. This is not good. This is not good at all. It's a huge waste of time, and it's potentially destructive to the lattice. So we did a little experiment, and we did different ion implantation times. We did 20 minutes, we did 30 minutes, we did 40 minutes, 50 minutes, etc. And we found that we only needed, I believe it was about 40 minutes. We didn't need that whole hour. So we were able to save about 20 minutes of ionization time for each wafer. That was a really big deal. And I guess the upshot of this little exercise is always question. If you have a process, don't think that just because you have a process that requires a certain set of parameters, that those parameters are needed. In this particular case, we were able to save quite a bit of time and heartache, and that was actually a big deal. Okay. I'd like to talk now about the 3 important particle distributions. They are the classical Boltzmann distribution and the 2 quantum mechanical distributions, the Fermi-Dirac and the Bose-Einstein. These are derived in some gory detail using probability theory and the appendix to chapter 3, plus a bunch of other stuff, which may or may not be of interest. Hopefully it is, so you can go through the mathematics, but here I just want to talk a little bit about some of the philosophy. So if we look at these 3 distributions, we can divide them in a rather broad sense into 2 areas, one classical and one quantum mechanical. The classical would be gas molecules, well, billiard balls, but gas molecules, air molecules specifically would be the example. They are identical. Every air molecule, which is oxygen, nitrogen, doesn't matter, they're essentially identical. You've seen one nitrogen molecule, you've seen them all. But they are distinguishable. Okay, we need to just see what that's all about. In quantum mechanical, they're also identical. Every electron is identical. Every photon is identical. But the difference is they are indistinguishable. So let's sort of take a deep breath and see if we can figure out what the difference between distinguishable and indistinguishable is. I'm going to claim that, say, nitrogen molecules are identical, but they are distinguishable not by what they are. They're nitrogen molecules. They all look the same. They all act the same. However, one nitrogen molecule may be over here, and the other nitrogen molecule may be over here. So I can distinguish them not by what they are, but by where they are, to the left and to the right. Now, can I do that in practice? Not very easily. However, just having the fact that they are distinguishable changes the rules of the game in the probability distribution and leads me to a completely different distribution. And this guy right here could be moving from left to right. This guy could be moving from right to left. Quantum mechanical. In quantum mechanical, they are indistinguishable. And the reason is that quantum mechanically, I should say, position and velocity are smeared out. That's the whole Heisenberg theory. The position is not something that I measure directly. I measure the wave function, and position is an operator, and velocity is an operator, and I cannot know position and or velocity with absolute certainty. So if I have two electrons that are close to one another and they're moving, I can't tell them apart in position. If I have two photons that are moving, I can't tell them apart with respect to position or velocity. So what's the difference then between electrons and photons? Fermi-Dirac says that I can only have two electrons in any given energy level. One spin up, one spin down. In Bose-Einstein, that restriction is taken away. So the difference between photons and gas molecules, the only difference is that with regard to photons, they are indistinguishable, and with regard to nitrogen molecules, they are distinguishable. And I just want to say one thing about photons. Photons are really, really hard to understand. And remember, I think it was in session 1, we said that Feynman has a quote that if you're learning quantum mechanics and you're not completely bewildered, you understand nothing. And he was probably talking about photons. So if you go back to the Bible, in the book of Genesis, what was the first thing created? I think it's the second verse. V'yomer Elohim v'hi or. And God said, let there be light. And guess what? There was light. Well, not the guess what. So photons are extraordinarily complex, and Bose-Einstein is not nearly as straightforward as either the Fermi-Dirac or the Boltzmann statistics. It's interesting, and I go over this in the appendix. The rules for Bose-Einstein are the same as the rules for putting cookies into identical boxes. They have to be identical cookies, and they have to be identical boxes. So you can't have chocolate chip, because chocolate chip, there's probably the chip is over here and one chip is over there. But if you have like oatmeal cookies and they're all the same and you put them into identical boxes, it's the same probability distribution as you get if you talk about the Bose-Einstein. The actual distribution here is a little bit more interesting, I think I'd use that word, than either the Fermi-Dirac or the Boltzmann. So let me give you an example of fermions that are not only identical but are indistinguishable. And these are my little fermions. And these are two of my grandchildren. They're sweethearts, and you'll notice they are identical. And if they're close by, they are indistinguishable. Now, this picture was taken when I think they were about 6 months old, maybe. Now they're about 3 years old. I cannot tell them apart. Their father, also known as my son, claims that he can tell them apart. I have to test him on that. I'm not really sure he can, but I definitely cannot tell them apart. However, if one of them is in the living room and the other one is in the dining room, it's not a problem. One's in the living room, one's in the dining room, I can tell them apart. However, if they're very close together or they're moving in the same direction close together, I can't tell them apart. So I like to call them my little fermions. Of course, I suppose I could call them my little bosons, but that doesn't sound very nice, so I'm not going to go there. Okay, so let's see. This is the classical Boltzmann distribution, and you'll notice that there's lots of, say, nitrogen molecules in the lowest state. You know what, I should say oxygen, because we like to breathe this stuff, so that's probably a little bit more useful. And then the distribution is exponentially decreasing as I go up in energy, and that's exactly what the Boltzmann distribution is all about. There are two forces here. The gravitational force wants to pull them down. Collisions, which have components in the positive energy direction, pushes them up. So it's this basically tug of war between gravity and collisions which creates this exponential decay. Now I could do the following. I could take this guy and I could put him down here. Is that okay? Well, I'm not in equilibrium. The whole idea is that the energy, which is really temperature, the total energy, is constant. Now I've reduced the energy by taking one of the higher energy states, a particle in the higher energy states, and bring it to a lower energy. That's not good. However, what I could do now is take this guy and bring him up here. So now I'm back in equilibrium. Now my total energy is constant. Why is this no good? Oh, look, we've got lots of particles, a little bit less, same number, a little bit less, and all of a sudden I go to zero. I've lost the smoothness. Nature hates jumps, quantum jumps. So that is the reason that this would, while it would be in equilibrium, it would have a quantum jump from finite occupancy to zero occupancy, and that probably would not work. So let me now go back to where it was, and that is not only in equilibrium, it's aesthetically pleasing, and aesthetically pleasing is a big deal. Okay, now I'd like to talk a little bit about the effective temperature on silicon doping as a function, I should have written this out, as a function of position. So let's say that we have a wafer. This is the wafer. I should have marked this right here. This is the silicon wafer. One end is at room temperature. Another end is at, say, 300 C. Hot plate. I can get easily 300 C on a hot plate. Now, this is N-type doped. The hot side, we've already seen that the Fermi level will go down. In fact, 200 degrees C, it goes from 0.3 eV to 0.1 EV. So at 3 or 400 C, it's essentially intrinsic. Whereas the room temperature, if it's, say, 10 to the 15th, is 0.3 EV above intrinsic. So if I put a digital voltmeter on the cold side, where's the cold side? Over here, I should get a negative voltage with respect to the undoped hot side, because the undoped hot side is essentially intrinsic, whereas the cold side is heavily n-doped. So if we put a positive terminal on the n-doped, I get a negative voltage. Suppose I get a positive voltage. If I get a positive voltage, well, using the whole idea of standing on your head, I would probably think, a reasonable guess at least, would be that it's p-type rather than n-type, and that indeed is the case. So this particular little experiment here, and I actually do this experiment in class, and it's very easy to do. We just take a silicon wafer, hot plate, and put a couple of books underneath one end as a support, and take a voltmeter, and you can actually do this. And this becomes the basis of what we're going to be looking at when we look at non-equilibrium. So I'll just ask the question right now. Is this thing in equilibrium or is it in non-equilibrium? Think about it for a second. Well, okay, I'll tell you the answer because we're running out of time. It is in thermal non-equilibrium because hot, cold, this maintains cold, this maintains hot, there will be heat transfer from the hot to the cold. That by definition is thermal non-equilibrium. However, it is in material equilibrium. There's no charge flow. Why is there no charge flow? Well, this is a very high impedance, the DVM. So we're not going to get any charge flow between here and here by way of the circuit, and there's no external circuit, so there is no charge flow. And what we're going to show is that the Fermi level is horizontal and straight, and materially it is in equilibrium. Okay, so unfortunately we don't have time for examples right now, and that's a bit of a shame. So let's go to a video clip. The same group, Peter, Paul, and Mary. We're going to see Paul initially, just as we saw Paul in the initial blowing in the wind video. 35 years later, this was 1965. I believe this is about close to 2000, maybe 1988, 1998, 1999. And they're just as wonderful and just as inspirational and just a joy. So Peter, Paul, and Mary, this land is your land.
And I rambled, and I followed my footsteps from the sparkling sands of a diamond desert, and all around me I heard a voice. All around me I heard a voice singing. Yes, this land was made for you and me. This land is your land. This land is my land. From California was cloud rolling, fog was lifting, and I heard his voice singing, it might have been Woody, this land was big, you and me. You do what, man? California, to the New York Island, from the Redwood Forest, to the deep water, this land was made for you. This land was made for you and me. One more time, this land is yours, your land, my land, California, California, this land was made for you and me. Your world, this land was made, and it still is, for you and me.
We at PBS have presented